Welcome to lecture 38 on risk management and insurance. In this lecture, we introduce the concept of a copula. Let's begin with an interesting statistical proposition. This graph we did in the last lecture. So down here we have the Pro-V density function. If you integrate, you get the cumulative distribution function, and the opposite if you differentiate, you're back to the PDF. The example here is a normal distribution. So the variable x down here has the normal distribution. The question then is, what is the distribution of those function values here on the upper axis of the cumulative distribution? So think a bit about that one. Down here, the variable x is normally distributed. And then up here in the cumulative distribution function, let's look at those values here. Between 0 and 1, those probabilities, what is the distribution of those numbers, of those values? Now, when I give this class in a classroom setting, sometimes, rarely, I have a student who can answer it. But it's actually something that you find in statistics books, but it's not used very much. The distribution that you have here is the uniform distribution, the standard uniform distribution. You see, it goes from 0 up to 1. That's the domain of that distribution, and it will be the uniform distribution. And it does not matter here. We have here a normal distribution. If you have here a skewed distribution, maybe a gamma distribution, you still get up here in the function values, you will get the uniform distribution. So whatever distribution you have down here for the variable x, the function values of the CDF will be uniformly distributed between 0 and 1. Okay, that's quite a surprising proposition, but it's completely central then for the understanding of a copula. Remember, the uniform distribution looks like this. So that's a PDF of a uniform distribution. It's just this rectangle. It's uniformly. So each, you always get the same probabilities for each little interval here. So this proposition is called probability integral transform. But that's a bit of an awkward name. And basically here, I'm just restating what I said before. So let's consider a random variable. That's what we have on the lower axis with a strictly increasing cumulative distribution function. So we will have an inverse. That's important here. So we must have a well-defined inverse. And we only have that if the CDF is actually strictly increasing. So define a new variable, random variable set. Now this set is just a value of the CDF. Which is this set is what we had on the upper axis in the graph before. You see that's the fx, and up here, that's those function values here now are the sets. So I could actually write here set equals fx here. So set equals fx. Those are the function values of the CDF. Then set has the uniform distribution, okay, like this. So it's just restating what I said before. So actually, the CDF transforms the X variable into a standard uniform variable. And this holds for every CDF that has an inverse. So it holds for the normal distribution, but it holds also for the gamma distribution. It will hold for any CDF that has an inverse. So what we do here, you see this X here, is those X variables, those values are transformed by the CDF here. They are transformed by this F function into the Z variable, and the Z variable is uniformly distributed. And now here you also see why this awkward name, probability integral transform. You see, you go here from the PDF to the CDF, you go through integration. Integration brings you from down here to up here. So that's why it's called probability integral transform. We transform the variable x, we integrate here, that's the CDF, and then, okay, we have here the transformed variable z, okay, and that one is uniformly distributed. Okay, it's a remarkable proposition. And it's easy to prove. The proof I have out of the Rice book, which is given at the beginning of this chapter. So let's calculate probability that the Z variable is smaller than some critical value. And for the Z, I'm just plugging in from the preceding slide, I'm plugging in the fx. Which is a set here according to equation 11 is the fx. So z is fx, I just substitute this in. And now apply the inverse f. So if you apply the inverse f here on the left side of the inequality, you get here just the x. F to the minus 1 of f, so the f just drops out. And then you have naturally also the inverse, you have to apply it on the right side of the inequality. Okay, so I have here now the f1. So I take here the inverse function. So I take here the inverse function on the left and on the right. So on the left it just drops out, and on the right I have now the inverse function. And then just remember the notation for CDF. The probability that x is less or equal this value here. So that's actually what the CDF shows. You see, we had before in the notation maybe px is smaller or equal some small x, and then you just had the small x down here. So that's what we discussed actually in the last lecture at the beginning. You see, so CDF is a probability that x is smaller or equal to some critical value x. So here you have the critical value x. Now here I have something more complicated, but it must then also appear here. This was in equation 1 when we defined the CDF. So here, probably x smaller than that. Okay, so the f that you just get this here. This was a small x in equation 1. In equation 1, that's a small x here. And okay, f and f minus 1, so that drops out, and so you just get the set, the small set here. And so probably that so random variable set is smaller or equal than some critical value, is just the critical value itself, and that applies to the standard uniform distribution. That's what we discussed last time. let's look at it. Yeah, here we have it. So probability that U is less than or equals than critical value is just the critical value itself. Okay, so that applies, okay, for the uniform distribution. That defines you the uniform distribution. So that's why you have here a 45-degree line. So probability U less than or equals than critical value is just the critical value itself. And that's in the uniform distribution. And that's what we showed here. So probability is a set smaller or equal small set is just the critical value small set itself. So that's a uniform distribution. So set has a uniform distribution. Okay, so the proof is actually not such difficult. Okay, so that's a remarkable proposition that is completely critical for the understanding of Copulas. If you have some distribution here, x, and then the CDF transforms those values, x, it transforms them here in the function values. You can call them set if you like, and those values here will be uniformly distributed. So that's this probability integral transform. It's called probability integral transform because through integration you get from the PDF to the CDF, and you transform the variables, okay, from the x into those uniform values appear. Now, proposition 2 is the so-called quantile transform. We also will use that one, not so much, but it's also actually used when copulas are explained. So let's also understand that. So so random variable U have the standard uniform distribution over the domain or over the interval from 0 up to 1. Remember, that gives you always a 0 to 1 with uniform distribution, gives you just the interval over which the uniform distribution is defined. With a standard uniform distribution, it's just from 0 up to 1. And let's then have the inverse of it. Let's take the inverse of it. Then the CDF of this x value here is actually fx. So original CDF fx. So let's begin with a uniform distribution. Let's take the inverse of it, and okay, then this value, let's call it x. Then the CDF of that random variable x is just actually the original CDF fx. Now that's almost that's actually almost does not require a proof, because you see, it's common sense. You see the inverse function, f2 minus u, so here's the inverse function, transforms the uniform variable u into a random variable x with the CDF fx. We just go backwards from the problem before. So we begin here with the uniform distribution, and then we go to the inverse of the CDF. So we come from here, we go to the inverse, and then we have the x values, and those x values have actually then the CDF fx, which is up here. So here you make the argument, you start up here in the second proposition. You have those uniformly distributed values here, and then you apply the inverse of the CDF. You see, you begin here, okay, applies the inverse, and then you get the x values, and those x values here that have actually this CDF fx. Okay, so it's basically just doing everything backwards. So So the inverse function transforms then those u values into x values which have the CDF fx. So it's actually pretty obvious what's going on here. But let's do also the proof here. It's out of the Rice book. So let's calculate the probability that x is smaller or equal to some critical value. And then for the x, I'm plugging in this up here. For the x, I take this from up here. So I have here the inverse of u. And then apply the f function on both sides. So f of f minus 1, it drops out. And here you get the f function. So on the left side, I'm applying now the f function. On the right side, I also apply the f function. So here it appears. And here's the f and f minus 1 matches and drops out. And because the u is uniformly distributed, this that just must be fx down here. You see, since u is uniformly distributed, you get here down here fx. That's again from the definition of the uniform distribution. You see, with uniform distribution, fu is just equal to u. Here in equation 5. You have the 45-degree line. So here, the fu is smaller than fx, so you just get here this critical value than fx down here. So that's this last step holds because u has a uniform distribution. You just get the fx here. So the fx that's a probability that x is smaller or equal than x is fx. Okay, so that's what we said here. So x has the distribution, the cumulative distribution function fx, the original one. So that concludes the proof. But it's maybe better if you just understand here what's going on with the quantile transform. You see, you begin here with the u's, and you go to the inverse function, okay, and then you have the x's, and those x's have the distribution fx. Okay, so that's pretty obvious here. You see it. It's called quantile transform. Here we start with the u's. Okay, so I have here actually. So I start here with the u's. I write it now down this way, and then I go and I'm getting here the x's. Okay, and that's actually it's a quantile function, you say, but it's the inverse. Okay. Now let's go to the copulas. Now a copula is simply a distribution function with uniform marginal distributions. And if you want to write down the CDF of the copula, okay, I do it here in equation 18, but naturally you can also write down, and later we will also write down the PDF of the copula, the probability density function. But I begin here with the CDF, the cumulative distribution function of the copula. So you have here a distribution function. Those are the critical values here. So you use this notation here for the copula. This C here stands for the F. So I have here the distribution function. That's a cumulative distribution function. Let's go back to the earlier notation. you see here, if I have a cumulative distribution function with two random variables, so the probability x is smaller than critical value x, y is smaller than critical value y. So I have here x1 and I have y here. I could actually write also here x1, x2. Okay, here I call it here x and y, but you can call it x1, x2, or whatever. So I'm using this notation here for the copula. So copula, now here I don't call it here x1, x2, I call it here u1, u2, and so on, because those actually are uniformly distributed. The marginal distributions of the copula are uniformly distributed. Then you speak about the copula, and for this joint distribution function, we take a capital letter C. We don't take a capital letter F. But if you prefer here to take an F, okay, so that's naturally, it's just a convention that we take a C. Okay, you can also take an F, maybe with a subscript C or something like that. Okay, but it's common notation for the CDF of a copula, just to use here the capital letter C. So that's a probability that random variable 1 is less than this critical value up to the random variable D. I'm now actually considering here now D random variables. Okay, that this one is also less than the critical value. And then you just write here the critical value. So that's entirely the notation we had before for the cumulative distribution function. Okay, on purpose, I'm here a bit slow. Okay, so here for f, x, and y, probability x smaller than critical value, probability y smaller than critical value. Now here, we use now here a C, because the distribution function is a copula, and here we write u1, u2, because those random variables now are uniformly distributed. Those marginal distributions are uniform. Okay, that's the cumulative distribution function of the copula. So the copula is actually a mapping from 0, 1, actually in d dimensions. So you speak about the so-called hypercube, okay, into the range of the function from 0 up to 1, because that's naturally the probability. Probabilities must be numbers between 0 and 1. So here, this is the probability, okay, that okay, u1 is less than this value, u up to ud is less than that value. So that obviously then the function value of the C, okay, is in the interval 0 up to 1, because it's a probability. And because the u's are standard normal, now the domain of the function, for each argument in the function, the domain is actually the interval 0 up to 1. And we have d arguments, so we speak about the hypercube. Okay, we have d dimensions. Now, proposition 1 holds that the values fx of a univariate CDF are always uniformly distributed. That's this probability integral transform that we had. And in this Clark theorem, we apply this property of CDFs to the univariate marginal CDFs of a multivariate distribution. So because the marginal values fi are uniformly distributed, you can use them in the copula. Now maybe let's look at that. It goes back to this graph here, and So we have here a joint distribution between x and y. We have here some marginal distributions of x and y. And then those marginal distributions are actually not uniform. But what's uniform, if we do now the CDFs, okay, of the marginal distribution, that this would be the CDF of fx. So the values of these CDFs, they are uniform. So see, so they go here from 0 up to 1. And those values here will be uniformly distributed. And you can actually put those values into the copula. And same thing actually here. Okay, you go here also up. Let's now do here the CDF of the marginal distribution. So this goes from 0 up to 1. And then again, those values here are uniformly distributed. And you can put those values into the copula. So be careful. The marginal distributions are not uniform, or not necessarily, they could be, but they are usually not uniform. Maybe the marginal distributions, here's a gray, those gray histograms, maybe they are highly skewed, okay, because maybe they have a gamma distribution. So you actually could have any distribution. So maybe it's a gamma distribution. Now here I work with a normal distribution. What's uniform is the values, the function values of the CDFs of the marginal distribution. This one actually then would be so Fy here. So that's a Fy. So proposition 1 holds for the values fx of a univariate CDF that the values of the univariate CDFs are always uniformly distributed. And Sklar's theorem then applies this property of CDFs to the univariate marginal CDFs of a multivariate distribution. So what we have discussed here so here we did it just for a random variable, for a single random variable, and we said what's on top, okay, is uniformly distributed. So that here is uniformly distributed. Now you can apply this now to the marginal distributions. You see here, the marginal distribution again is again univariate. I have here a bivariate random variable, but the marginal distribution is univariate, and those values here of the marginals are uniform. And because they are uniform, I can put them into the copula. So because the marginals are uniform, here I call it Fi, because I have D marginal distributions. I use here with a joint distribution with D random variables. Before I just use 2, X and Y. Okay, here I use, okay, but here I use, I go up to D. So you can use them in the copula. So you see in the copula, the distribution of the random variables must be uniform. Okay, so here we have the definition of a copula. It's really a little bit something, okay, that one has to discuss. It's not difficult mathematically, but one requires a little bit of imagination here. So maybe you listen to this lecture twice. Now I do this Clark theorem. Given the joint CDF, okay, I have here a joint CDF of a joint random variable up to D random variables here. We have continuous marginal distributions. Remember, the values of those marginal distributions are uniform. That's very important. So the values of those marginal distributions here are marginal CDFs are uniform. Okay, not those values here, but if you go to the CDFs, then you have uniform values. So you have a unique copula. So you can express any joint distribution function. You can express it actually as a copula of its uniformly distributed marginal CDFs. So what I have here are the marginal CDFs, and those marginal CDFs, U1 up to UD. Yeah, okay, should be UD here. Yeah, okay. Okay, that's a copula. So we can actually put those values of the CDFs of the marginal distribution, we can put it into copula, and then actually we get the original joint distribution here. So that's what the Clark theorem pretends. And also the converse is true. So that's important. The Clark theorem implies that every multivariate CDF can be expressed using its marginal, every multivariate CDF can be expressed using its marginal CDFs Fi and the unique copula CDF C. You see that's a UI here. And the copula, if I use a capital letter, I just mean for the copula, I mean the CDF. So here, I mean the CDF. If I use a small lowercase c, then I would actually mean the PDF of the copula. Now, this makes it possible to separate the modeling of the marginal distributions from the modeling of the dependent structure among the random variable. You can actually model the marginal distributions using any continuous CDF, and then the copula will capture the entire dependent structure among the random variables. So we can express any joint distribution. We can express it as I have here a CDF of the joint distribution. I can express it as a copula CDF of the values of the marginal CDFs of that original distribution. And this copula function here actually will be unique. That's what the Clark theorem says. So we can first, so when you have a problem like this, you can first model here those marginal distributions. Then you can calculate those U values here, those uniformly distributed U values. And then actually you can try to find the copula, the copula CDF. So you go in 2 steps. First, you look at the marginal distributions, and then actually, okay, that's an easy problem. Okay, you have those histograms here, and then you look for those U values here. They actually are called pseudo observation. You look at those pseudo observations, and then you actually look which Copula CDF best fits the data. Okay, that's so then you try to find out the Copula CDF. The Copula CDF is actually unique according to the Sklar theorem. Okay, I would like to finish this by just deriving this Sklar theorem, at least this equation 21. The full proof of Sklar theorem, you have to go to McNeil and to the book. But let's just derive shortly equation 21, which tells that any joint CDF we can actually write down as a Copula type CDF of the U values of the CDFs of the marginals. Now, according to the probability integral transform, this is proposition 1, so the set values of the random variables defined by the marginal distributions are uniformly distributed. It holds for every univariate random variable. We call this X, we call this Z, okay, when we saw it for the first time. Now here I apply to the marginals. The marginals are also univariate random variables. So here I call it now X1, and here as a U1 and the X2 and the U2. Okay, you have all those marginal distributions, and their function values of the CDFs of those marginal distributions must be uniform. Now it follows. Now let's write down here the joint distribution. So that's just okay. What's a joint distribution? That means okay that the probability X is smaller than the critical value X1 and so on up to D. Okay, that's what the joint distribution okay shows. That's just a definition again of the joint distribution. And now let's apply here the F1 function. So if I apply here the F1 function to the X1, then I get the U1. So I apply the F1 function here according to 22, I'm getting here the U1. If I apply the F1 here, okay, yeah, okay, you just write it down here. And you go up to the FD. Okay, so you apply here the FD, you get the UD, and again the FD here, okay, naturally you must just write it here. And then, okay, because that stuff here is uniform, you just get again here, this value here goes here. Probably, remember, in the uniform distribution, probably U is equal or less than critical value U lowercase. You just get here the U lowercase. Now here I have another expression. So this expression just must be the same as that expression, because here I have the uniform distribution. But that proves it. That's already the derivation. You see, here the joint distribution here of those D number of random variables can be expressed as a Copula, okay, and that's equation 21. So, okay, Copula, and here, okay, the values of the uniform distributed values of some marginal CDFs. Now that's not the full proof. You see, you need here necessary and sufficient conditions. So you have to go, okay, actually to McNeil's book to do that. Now I will apply Copulas the next time. The ideas are not so easy. Copulas only became popular in research over the past 15 years. the Sklar theorem is older, but then actually copulas have not been used much. And in finance, it really took off around the year 2000. And okay, in economics, people even do not use it now. But in finance, copulas are now really the main tool to model joint distribution functions. So for example, if you have a return to share 1, share 2, share 3, and so on, you can now look at the joint distributions, and you model those joint distributions of the shares in a portfolio. Maybe you have D number of shares. You can model that joint distribution of their returns, okay, using the copula approach. Also in insurance, you can do that. Let's assume we have here the loss from insurance product 1, and the insurance company also then sells different types of insurance contracts. Then we get here the joint distribution of the losses of the aggregate losses of the insurance company. So we can model this nowadays with copulas, and it's very popular. There's a lot of active research going on here. So we don't have to use the convolutions. Remember, we already have seen this problem. When an insurance company has different products, if it sells different types of contracts, you can use the convolution we said in the chapter on insurance supply if those contracts are independent. Now here I'm more general. The contracts here are not independent, and that's why we look at joint distributions, at the joint loss distribution of all contracts together. If the contracts are independent, okay, maybe fire insurance and and health insurance, okay, maybe those two types of contracts are independent, then you can actually do the convolution approach that we discussed earlier. But here we are more general. Okay, here we look at the joint distribution, joint probability distribution of all contracts, all types of contracts of the insurance company. And it also holds for a portfolio for different shares. Naturally, shares interact. And so here you can actually look at the joint distribution of the returns of all your shares in the portfolio. So it's something very popular, but it's quite new. And it's still a lot of research actually going on here. Okay, I return to this next time. We have to discuss this a little bit more because really so much work is now just being done on this. Okay, thank you very much.